In this video, I will describe how to do inference for one proportion. We'll start with confidence intervals. When we use a confidence interval, the first thing that we do is we calculate p hat, which is the point estimate for p. So p hat is just the sample proportion, calculated by taking the number of successes in the sample divided by the total number of observations. A confidence interval for p will tell us how close we expect p hat, our sample proportion, to be to p, our population proportion. The formula for doing a confidence interval for p looks like this. We have p hat plus or minus the square root of p hat times 1 minus p hat over n. And when dealing with confidence intervals, this z star value, there are some pretty common levels for confidence, 90, 95, and 99. So it can be helpful if you just keep a list of these z star values so you don't have to reinvent the wheel and find them every single time. The requirements for doing confidence interval for one proportion are that both of the following must be true. N times p hat has to be greater than or equal to 10, and n times 1 minus p hat also has to be greater than or equal to 10. And just pay special attention to the fact that we're using p hat here in these formulas because it's going to be a little bit different when we talk about hypothesis tests in a couple minutes. So here's an example. The quick service restaurant magazine Drive-Thru Study visits restaurants in the largest fast food chains in all 50 states. During each visit, the researcher ordered a main item, a side item, and a drink. One item was left off of each order. For example, a sandwich was ordered without pickles. After receiving the order, it was checked for complete accuracy. Anything that was not exactly right, including other things that were asked for, such as napkins or condiments, resulted in the order being classified as inaccurate. In 2012, Chick-fil-A had the highest number of accuracies. 251 out of 274 orders in the sample were filled accurately. Give a 95% confidence interval for the proportion of all orders filled accurately by Chick-fil-A. All right, so if we're going to do a confidence interval for this, the first thing we start is by calculating our sample proportion p hat. So the sample proportion is calculated just by taking the total number of successes in the sample. In this case, that's going to be that 251 accurate orders out of the total number of orders, which was 274. So we get a sample proportion of 0.9161. Next, we're going to go ahead and plug everything into our confidence interval formula. So we're going to plug in the p hat. We have z star. Now it said we wanted 95% confidence. So if you recall our table from earlier, z star for 95% confident is equal to 1.96. And then our sample size is that 274. So plugging everything in and then working everything out, we end up with a margin of error of 0.0328. So I'm going to take 0.9161 minus 0.0328 and then plus 0.0328 to get the upper and lower bounds of my confidence interval. So in this case, I have 0.8833 to 0.9489, or you could think of it as 88.33% to 94.89%. Next, we check to see if we meet the requirements. Remember, both n times p hat and n times 1 minus p hat, both those quantities need to be bigger than 10. So I plug in the values I had for n and p hat into those equations. I get 251 and 23, which are both bigger than 10. So we do meet the requirements for this confidence interval. So in conclusion, we would say we are 95% confident that the proportion of accurately filled orders at Chick-fil-A is between 88.3% and 94.9%. Now, we just did all the work by hand, but in these chapters on proportions, there is a really awesome Excel spreadsheet that can help us do the calculations as well. And if you've been one of those SPSS haters, then you are going to love this Excel spreadsheet. So here's what the spreadsheet looks like. And basically, you need to input all of your information into the inputs box over here on the left. So I put in X, that's the number of successes. It's the number of accurately filled orders in this case. Put in my sample size N, and I put in my confidence level of 0.95 because I wanted a 95% confidence level. The Excel spreadsheet will also check our conditions for us. So it does all that math for us. We just look here and make sure that both of those are bigger than 10, which they are. And then the confidence interval is going to be down there right at the bottom, 0.883 to 0.949. You can see this is exactly what we got when we calculated it by hand. It just is a lot faster and easier using this fun Excel spreadsheet. So we also can look at p hat, which is the point estimate, again, for p in when we're dealing with proportions. All right, so now let's look at hypothesis testing. When we write the hypotheses for a hypothesis test for one proportion, null hypothesis is that p is going to be equal to something, whatever's being claimed in the problem. And the alternative hypothesis then is that p is either greater than, less than, or not equal to the something. Again, the greater than, less than, or not equal to will be determined by the problem, as will, I've called it p naught here on my slide, but I'm just saying, hey, that's the value that we're claiming under the null hypothesis. When we're dealing with proportions, sometimes the distinction between the different symbols can be a little bit more tricky because they all seem to have a p in them. P, p hat, p naught, p star, p1, p2. So there's lots of p's to keep track of. So one thing I always try to remember to help me write the hypotheses, I just say no hats in the hypotheses because the hats represent values from the sample and those would never be in your hypotheses. The test statistic is a z statistic, p hat minus p, which is the value claimed under the null hypothesis, divided by square root of p times 1 minus p over n. So we're going to work this the same way that we found test statistics and p-values back when we were dealing with means. So we're going to find our z-score and then use the normal applet to help us find the p-value. The requirements for hypothesis testing are similar to confidence intervals, but a little bit different. So hypothesis tests require that both n times p and n times 1 minus p are greater than or equal to 10. So in this case, we use p, the value of p under the null hypothesis, to plug into our requirement formulas. Here's an example. In 2012, Chick-fil-A had the highest number of accuracies. 251 out of 274 orders in the sample were filled accurately. Is there evidence that Chick-fil-A is more than 90% accurate? So we start by writing our hypotheses. So under the null hypothesis, we're going to say p is equal to 0.9, or 90% in other words. And under the alternative hypothesis, we're going to say that p is greater than 0.9, because this is what we're trying to prove. We want to know, if you look back at the problem, more than 90% accurate. So I start again by calculating my sample proportion, which is the same as the previous example. So I take the 251 over 274 and I get the 0.9161. Next I'm going to calculate that test statistic using our formula. So I plug everything in. Notice that in the denominator of the formula we're using p, the value that's assumed under the null hypothesis, rather than p hat. If we do all those necessary calculations, we end up with a z-score equal to 0.8883. So now I'm going to use the normal applet to help me find the p-value. Because I was interested in showing that Chick-fil-A was more than 90% accurate, that's greater than, so I'm just going to shade that upper right tail after I enter in the z-score, and that's going to give me an area of 0.1873, and that's going to end up being my p-value. Next, we need to check our conditions. So we take n times p and n times 1 minus p, and both of those quantities need to be greater than or equal to 10. So again, just pointing out that we're not using p hat when we're talking about the hypothesis test requirements. We use the value of p assumed under the null hypothesis. So in this case, both those quantities were easily bigger than 10, so we do meet those requirements. With a p-value of 0.187 then, our conclusion would be that we fail to reject the null hypothesis. We have insufficient evidence that Chick-fil-A's accuracy is greater than 90%. We can also do this calculation in Excel, And you will be able to use this Excel spreadsheet on the exam. So you can actually use it to double check your handwritten calculations, or you can use it to do all the calculations on the exam. You're going to have it available to you. So we enter in the appropriate things over in the inputs. We have our number of successes and our sample size. This time for our hypothesis test, we want to make sure to fill in those bottom two. The value assumed under the null hypothesis, which in this case was 0.90, which is equivalent to 90%, and the type of test we were interested in greater than. So there's like a little drop box there in Excel that allows you to choose greater than, less than, or not equals to. It will check the requirements for the hypothesis test here as well. We're just checking to make sure that those are both greater than or equal to 10, which they are. And then it gives us the test statistic and the p-value. Sometimes before we begin a study, there's a certain margin of error that we're hoping to achieve when we do our confidence intervals. So we can actually calculate what sample size we need to get that specific margin of error. So here's an example of how that works. PTC is a substance that has a strong bitter taste for some people and is tasteless for others. The ability to taste PTC is inherited. About 75% of Italians can taste PTC, for example. You want to estimate the proportion of Americans with at least one Italian grandparent who can taste PTC. Starting with the 75% estimate for Italians, how large a sample must you collect in order to estimate the proportion of PTC tasters within 4% with 90% confidence? All right, so we have this formula. It's basically the margin of error formula for one sample proportions that's been solved for n. Everything's just kind of been manipulated around to solve for n. So it's n is equal to z star over mu, that quantity squared, times p star times 1 minus p star. That'll give us the sample size we want for our desired margin of error. So z star is going to be based on the confidence level that you want to have. So in this particular case, we were looking for 90% confidence. So z star for 90% confident is 1.645. Next we have m. M is our desired margin of error. It's going to be given to us in the problem. So in this problem it says we wanted to estimate within 4%. So that 4% is the desired margin of error. Now something that's important to note is that everything that we put into this formula must be in decimal form. So the problem over here said 4%, but when we put it into the formula, we want it to be in decimal form, so 0.04. P star is your best guess for what P is. Oftentimes there's things like pilot studies or previously collected data or things like that that can help you have at least an idea of what you think P is going to be, which is the case with this one. It told us to start with the 75% estimate for Italians. In situations where you really have no idea, then the most conservative estimate for P star is to use 50% or 0.5. So in this case, we're going to start with that 75% there. And again, everything that goes into our formula must be in decimal form. So I'm going to use 0.75 in those calculations. So here's my equation with everything plugged into it. I can go ahead and work out those numbers. Let me tell you that in working these numbers out, something that's commonly forgotten is this little squared symbol up in the corner here. It's small, it's little. By the time you plug everything in, it's easy to forget. So don't forget to square that part. Once you make all the appropriate calculations, you get 317.112. So does this mean you should sample 317 people plus maybe just the right arm of the 318th person? Of course not. Okay, so we're going to go ahead and sample that whole person. For sample size, we always round up. So we take the whole person. So even though general rounding rules would say round down on this one, we are going to round up and use the entire person. So we need a sample size of 318.